So we've established the definition of the null space of a matrix. If our matrix has n columns, the null space consists of all vectors with n coordinates that satisfy the equation A times V equals the zero vector. So keep in mind, it only makes sense for a vector to live in the null space if the vector has the right number of coordinates. So if we view our matrix as a machine that goes from Rn to Rm, we can think of the null space as some collection of vectors that lives inside of R to the n. The mathematical notation we use for this is this sideways U notation. So we write null of A, sideways U, R to the n, to indicate that the vectors in the null space all have n coordinates. Now, of course, not every vector with n coordinates lives in the null space. The way we distinguish between vectors that do and do not live in the null space is by checking the equation A times our candidate vector equals the zero vector. But this notation, null of A, sideways U, Rn, is used to indicate that some of the vectors in Rn are in the null space. So here are two sort of generic shapes of matrices one might come across. On the left here, the matrix A has a shape given by, let's see here, 5 by 4. And on the right, this matrix B has shape given by 3 by 6. So A on the left here is a 5 by 4 matrix, which means that the null space of this matrix lives inside of R to the 4 because this matrix has 4 columns. For B, since this is 3 by 6, the null space lives inside of R6 because this matrix has 6 columns. Okay, so here's another example. So here we have an example of a 4 by 2 matrix. And since this matrix is 4 by 2, we know that the null space lives inside of R2. Now, if we wanted to take a closer look at the null space, what we could do is we could systematically describe all vectors in the null space by solving the system Ax equals the zero vector. And all we really need to do this is find the reduced row echelon form of our matrix. So here what we're finding is that the reduced row echelon form of our 4 by 2 matrix is this matrix where we have 1 and then a bunch of zeros and -2 and a bunch of zeros. Remind yourself what this means. What this means is that our original matrix had a second column that was -2 times the first column. So we can systematically describe every vector that solves Ax equals the zero vector here. And what this ends up being is just all scalar multiples of the vector 2, 1. So what does this null space look like for this example? Well, the vectors in the null space live in R2, and we can visualize R2 if we want. It looks like the two-dimensional axes. And, the vectors in the null space are not every vector in R2. They're every scalar multiple of the vector 2, 1. So the vector 2, 1 looks like this. And then if we collected all multiples of 2, 1, we would be looking at a line in R2 through the origin. So the null space of this particular matrix looks like this line in 2 space. What else are null spaces useful for? Remember when we discussed directed graphs, we said that paths in a directed graph can be represented numerically by path vectors. So here I have an example of a directed graph on 3 nodes and 4 arrows, and I've written down 2 path vectors that describe different paths in this directed graph. Let's look at this first path vector here. The first entry is a -1, and remember, this -1 is saying that in the path we're about to describe, we will travel against the arrow A1. So maybe we start at the node V2, and we travel against A1 to get to the node V1. And we also have a 1 in the 3 position, which means that in our path, we traveled with A3. So that takes us from the first node to the third node. So that's the first path. We start at V2, go against A1 to get to V1, and then we go with A3 to get to V3. Here on the right here, we have a different path vector. For this one, we have a -1 in the first position, which means that in this path we traveled against A1. So if we do that one first, that would take us from V2 against A1 to V1. We have a 1 in the 3 position, which means that in our path we traveled with A3. So maybe that took us from the node V1 to V3. And then we have a 1 in the 4th position, which means we travel with A1 for this path. That would take us from V3 back to V2. Now, remember, the incidence matrix of a directed graph is an n by n matrix where the number of rows is the number of nodes and the number of columns is the number of arrows. Well, what this means is that we could take our incidence matrix and multiply by the path vectors we've constructed here. When we take the incidence matrix of our directed graph and multiply by our first path vector, we produce the vector 0, -1, 1. And when we take our incidence matrix and multiply by our second path vector here, we produce the 0 vector. So that's kind of interesting because so with our new language, the way we can phrase this is we can say that the first path vector does not belong to the null space, whereas our second path vector does belong to the null space. And of course, if we take a closer look at our two paths here, the first path was definitely not a cycle. It just took us from V2 to V1 to V3, but we didn't wrap back around. Whereas our second path here took us from V2 to V1 to V3 back to V2. The second path here was a cycle, and the first path wasn't. And this is kind of interesting because the second path vector lived in the null space, but the first path vector didn't. And this turns out to be a theorem. So in the first homework assignment, or at least in the problem set on directed graphs, there was a problem like this, where you had a path, and the path turned out to be a cycle, and I actually had you go through and calculate the incidence matrix multiplied by that path vector, and you should have noticed that you got 0 when you did that. This is a theorem, and in fact, it's a theorem that completely categorizes paths in this way. I guess by that what I mean is this theorem categorizes all cycles, and what the theorem says is that a path is a cycle if and only if the path lives in the null space. So if you're like studying a very large directed graph, and someone gives you the path vector for some path in that directed graph, if you wanted to check whether or not that path was a cycle, it would actually be a difficult problem to try to visualize your enormous directed graph and figure out where the cycle took you. Instead, what you could do is you could take your incidence matrix, multiply by your path vector, and check whether or not you got 0. And what you're really doing is you're checking whether or not that path vector is in the null space of your matrix.